Well, hey guys, today I'm just doing some circuit play, making a output stage for an op amp, so you have a little audio amplifier. Why do this when you have chips that can certainly work? Well, this is learning. This is just for fun. In fact, this circuit is untested yet. As of yet, I need to run a bunch of tests on it and see if it's even going to work. I build it up here on the board. Just an 8 ohm load connected to the output. Just doing the DC checks, making sure I'm getting, just make sure it's working as far as DC goes. Getting the bias set and everything. So let me describe what's going on here. Well, this is your typical complementary symmetry type push-pull audio amplifier output stage. Pretty basic. I'm using what's known as a complementary feedback pair instead of a Darlington type output. And I think I drew it here. This is your Darlington output stage, where you have two of the same polarity transistors, but the complementary feedback pair is kind of interesting because here I'm driving this PNP with a NPN, and the bottom section is a PNP driving an NPN. So why would I use this? Well, for one thing, in the biasing section here, there's only one base to emitter junction voltage drop, so I just need two diodes in the biasing network, one for the upper, one for the lower. And since the Darlington has two base to emitter junctions, the forward voltage is around 0.7 volts, that's 1.4 volts, so I need two diodes, upper and lower, 4 total. I mean, I could use a transistor here and set the bias that way, but I'm just using diodes here and using these resistor values to set the bias. Okay, so how does this complementary feedback pair work? Well, it's kind of interesting. What happens is, current's going to flow this way, and I'm using conventional current flow versus electron current flow. So current flows this way, but it can't get through this collector of this transistor. Now if I turn this transistor on by putting some bias on this base here, now current can flow through this transistor and down. And now that current is flowing through this emitter to base junction, this transistor turns on. So that's pretty much how it works. And because this transistor is in the collector to base of the output transistor, it's in the collector to base circuit of the output, it's got some negative feedback. The complementary feedback pair has more linearity. A little bit, you give up a little bit of gain for more linearity. Plus, it's more thermally stable than a Darlington pair as well. So that's why I'm using it here. Well, a couple more things before I continue on. The output stage here, as shown, whether I use Darlington or this type of arrangement, the complementary feedback pair, is a current stage. There's no voltage gain stage. So I have to get all the voltages as high as I can before I feed it in. So that's why I'm going to use an op amp, do all the voltage amplification up front, then shoot it into the current stage so I have a power amplifier. Well, one limitation of using an op amp is its supply voltage rating. The one I'm using, the LM4562, well, I might use an LM, what is it, a 338, I think, or 3, I forget. But I think it's like plus and minus 17 volts or 34 volts total. And you don't want to push up against that. So the maximum voltage of the circuit would be plus 15 and minus 15 volts. And of course, if you look for a op amp that has a higher voltage output, you can certainly increase that voltage. Now, another thing here is the transistors I have are not real powerful. The outputs here, they can handle continuously about an amp and a half. And if I use a plus and minus 12 volt supply with 8 ohm load, the maximum current would be, with a non-inductive load I should say, would be about 850 milliamps or so, maybe actually less because it can't swing all the way to the rail, so probably like 0.7 or 700 milliamps. So I possibly could squeak by 4 ohms because, you know, it's not, each transistor is not going to have a continuous current, and I think they're rated for more current if it's pulsed, because you know you have the peak on the positive swing and the peak on the negative. So yeah, I think we have a little bit of room, though realistically I would not recommend it. I'd go up to like a 5 amp transistor on the outputs. And if you're going to go with a higher voltage op amp, you know, say like plus minus 22 volts, definitely would have to use a 5 to 8 amp transistor if you're going to run 4 ohm loads. Well, I don't even know if this thing works. We're going to find out. Now I don't have the diodes connected to the transistors for thermal tracking, and hoping I can get away just on this breadboard because it's kind of hard to get those tied together. And one thing I forgot to mention about the complementary feedback pair is you mount the diodes to the driver transistor, because the driver transistor dictates the polarity of the entire circuit. Even though you're using a PNP here, this pair of transistor acts as an NPN. In fact, that's why the emitter degeneration resistor for thermal stability is in the, it's still actually in the emitter side, even though it looks like it's in the collector. Well, it is in the collector side of the output, but it's really an NPN transistor, and this is a PNP down here. Very important to understand that. Alright, it's time to test it out. I'm going to use my function generator, and there it is. You can see on the blue spectrum analyzer there is some distortion. That's probably mainly coming from this. This is not a low distortion device. And let me turn the supply voltage down. See, we're rail clipping now. Notice what happens when the voltage is turned down. You get these notches at crossover point. Yep, that's crossover distortion, because when I turn the voltage down, the current through the biasing network gets really low, and it doesn't quite fully turn the transistors on. I don't have a constant current source in the biasing network, which would help stabilize that, but what are we doing? That's running 500 millivolts, so that's 1, 2, that's 1 volt peak to peak, and you lose almost a volt in the transistor, so we're only running less than 4 volts supply. And as we bring it up to, let's see here, that's about 5 volts. Around 5 or 6 volts, the distortion is gone. So crossover distortion is a non-issue with the bias that I've chosen. So that's working pretty good. It's 4.7K resistors. Okay, well, I guess it's time to move on and see what happens if I connect the op amp up. Okay, I have an IC op amp plugged in there, and my music source. Here's what we're getting. I'm running 12 volts, plus or minus 6 volts. And it looks like there are some harmonics. You can see here. Now we're starting to clip. I don't have a potentiometer, so I can't fine tune it. I'll put that in later. I mean, it's not bad, but you have to remember, I'm running feedback local. This output stage does not have any feedback. In other words, it's not enclosed in the global negative feedback loop. So, you know, it's not bad. It's pretty linear. So what I'm going to do next is, you know, go global negative feedback and to see how the circuit performs. Okay, so what I've done is I included the feedback, well, the output in the negative feedback loop, like this. So this just represents the output. This is the op amp, and these are the values I used. Actually, I'm not using a cap right now, so there might be some DC offset. Normally you'd have a cap, but I didn't include one. Yeah, this is just play. I don't care if there's some DC offset. No big deal. In fact, I should measure that. And I also switched this chip. I had a LM833, and I switched to an LM4562. That's just a beautiful op amp. It can drive a little bit lower impedances. The 833, looking at the data sheet, seems to be around 2 kiloohms that it could drive, like the TL072. But this chip can handle 600 ohm loads. And it's a very fast chip as far as audio goes. It has a gain bandwidth product of 55 megahertz. I'm going by memory from the data sheet. A slew rate of plus minus 20 volts per microsecond. Extremely low noise figure. And incredibly low distortion. It's just a beautiful chip meant for audio. And I did switch it out mainly because it can swing closer to the rails. It can handle a little bit more load. You know, it gets loaded down a little bit from the output. This thing's starting to look like a mess with wires going everywhere. But let's see what we get here. Okay, oh yeah, I added a potentiometer so I can fine tune. And there's, of course, we're clipping and you get the harmonics. So we tune out the harmonics right to the point of no clipping. And we're running about 3.18 volts. Much better. I could get probably like 2.8 or 9 with the other chip. So much better. Let's see here. What did I say? 3.18. Square that. I'm sitting on top of something. and divide that by 8 ohms. That's our load. 1.26, getting close to 1.3 watts with a plus minus 6 volt supply. Is that good or bad? So, you know, that's a total of 12 volts, 8 ohm load. I estimate with a theoretically good amplifier, I mean accounting for the losses in the transistors and the degenerating resistors, emitter resistors, you'd probably get around 1.6 watts. So very happy, and that's using a Darlington. But with the current feedback pair, I'm actually impressed. I'm getting 1.3 watts. That's actually very good. And I also have to consider that I'm using 0.47 ohm resistors here, so you do get some loss there. So this thing is really performing right where it should be. Now let's take a look at damping factor. What's the damping factor of this circuit? Okay, I'm going to measure the damping factor. What is damping factor? Well, it's the ratio of the load resistance. It's usually measured at 8 ohms. 8 ohms. The ratio of that to the internal resistance of the amplifier, or internal impedance. Very easy to measure. You know, you just measure this, you can calculate the current and all that stuff, and then you can just use that to find this using Ohm's law. Very easy measurement. What I have done is set the amplifier to about 3 volts, and I've set it down to 40 hertz. And what I do is I'm going to take a measurement with the resistor connected and with it disconnected. Where'd my page go? You know, if I disconnect the resistor, the voltage should go up a little bit. And when I connect it again, it'll go back down. If, depending on the damping factor, if damping factor is infinite, okay, let me get a measurement. No change if it's infinite, but there's really no such thing. So we're running at 3.01 volts, and I'll connect the resistor. Did not change at all. See, it's connected now. How can that be? It's infinite. Damping factor is extremely, extremely high on this amplifier. It didn't change. Well, if I had, you know, more digits, if I went out to thousandths, 10 thousandths, yeah, you might see it change. You might be thinking, well, wait a minute, you have resistors in here, like these emitter resistors and the transistors themselves. You put more load, aren't they going to change? I mean, aren't you going to develop more current, causing more voltage drop? Well, yes, but you have to consider negative feedback. Negative feedback sees any change from that output and it's going to fix it. And that's exactly what's happening here. So our amplifier has an extremely high damping factor. And I'm not going to explain damping factor anymore, and how, you know, it affects speakers, resonance, and damping of the movement of the cone of the loudspeaker. We'll take a look at that in a later video. But just another impressive spec from this amplifier. Okay, I'm going to check frequency response next. Okay, frequency response. I bypassed this input capacitor. Normally I wouldn't do that, but I don't really have the right value in there to get a flat response down to 20 hertz. And I don't know if the frequency response of this is good. I think it is pretty good. But see here, running at 20 hertz and about 2.97 volts. So I'll leave it set and go up to a higher frequency. Well, I'll tell you what, I'll just run this sweep. I don't have all the frequencies to check, so let me start this thing over. We gotta, it's staying around 3 volts. We're already at 3 something kilohertz. Frequency's changing pretty quick, so the scope's probably not keeping up with it. Let me hit stop here. It says 311 there. I gotta change this. How am I? Oops. Yeah, it's staying pretty much at 3. What happened to my trigger level? Oh, it reset. Okay, well, frequency response is pretty flat. Probably as good as I can measure it using this thing here. Now I'm just checking stability. I pulled off these Miller capacitors. There's metal in them because they stick to my magnetized screwdriver. And that one's off too. I just pulled a leg off, kind of under the resistor there. And surprisingly, it was stable. Even in clipping, it's not oscillating or anything. But I really don't feel comfortable not using those. Especially when I start pushing power, cranking up the voltage, we're going to have issues, I would think. So yeah, I don't really want to run without those Miller capacitors. But it is still impressive that it is not oscillating or anything. Earlier I was playing around with it, and before I had the op amp on there, and yeah, I was getting definite ringing on the outputs there. Okay, I hooked the speaker up and removed that load resistor. Now you can kind of see the circuit a little better. I wasn't getting any output at first because I had the speaker connected one hole over to the right, which kind of confused me a bit, but now let's see what happens. How's our heat sink? I turned the voltage up. A little warm. I have to watch the stability because, like I say, I don't have those diodes near the transistors for thermal stability. But, you know, we have current limited supply, so nothing's going to happen really. Okay, music test.
Why do we accept this? Because we're a society built on wants, not needs. What are we talking wants from childhood? Big bank accounts, fast cars, plasma screen TVs, light consumption, or just useless furniture.
Connect it down again.
Social unrest.
Sounds just fine. I don't hear any problems. Okay, power test. 8 ohm load. I don't think this has the grunt for 4 ohm loads at that voltage level. Now I'm running it at plus and minus 12 volts. I got to be really quick because that's an inadequate heat sink, and we'll probably get over 5 watts. I don't know, maybe around 5. That resistor will get hot. I did increase these capacitors here because, you know, the cable distance here, and I kind of suspect something going on with this thing. I need to repair it or get a better supply. I noticed in some other tests of amplifiers using this thing. But anyway, go ahead and power it up. And quickly here get this thing adjusted. Right about there. And that's 6.53 volts. So I'll get this turned off. Now the bias here, it's running a little hot. I'm probably running the bias at 100 milliamps. And that's because, I turned up the voltage. And I really could increase the bias resistor values. But anyway, that's another thing. What was it? 6.53. I'm on top of something again. I can square that, divide that by 8. And about 5.3. Not bad at all. I think the maximum you get from an ideal amplifier would be around 7 watts, so it's actually doing pretty good. Not too bad at all. And well, that's it for this fun. Just wanted to play around with the output stage for an op amp. Thanks for watching.